Hey everybody, welcome to Data Umbrella's webinar. I'm going to do a brief introduction and Jeff will do his presentation and we'll open it up for Q&A. You can ask any questions during the presentation in the chat or Q&A and we'll get them answered along the way. This webinar is being recorded and will be available on our YouTube. A little bit about Data Umbrella. We're a community for underrepresented persons in data science and we are a nonprofit organization. This is our team. It's me, Reshma, and Beryl, and Christina, and Sandra, and Sangha. We have a code of conduct, and we thank you for helping to make this a welcoming professional community for all. There are various ways to support Data Umbrella. The first and foremost is to follow our code of conduct. You can share our events with other people. We'd love for other people to find out about our community and events. And you can also contribute to Data Umbrella. We have a brand new website that's built using Jekyll and Markdown and HTML. You can contribute to timestamps for our videos. We just had a PyMC Latin America sprint. We have a blog as well that is hosted on GitHub and a data events board. You can also support Data Umbrella by donating to our nonprofit. We are an open collective, and if you work for a company that uses Benevity, your company will match a donation that you make. All of our events are on the Data Umbrella YouTube, so if you want to subscribe to our channel for past events and upcoming events, feel free to do so. We have a lot of playlists. One of our most popular ones is career advice. We have data visualization, contributing to open source, scikit-learn, PyMC, and NumPy series are just some of these playlists. We also have a monthly newsletter. It's at dataumbrella.substack.com. Our website, which we just ported over, we're in the process of bringing some of our resources over, so that's going to be a little bit slow. We're on all social media platforms as Data Umbrella. Meetup is the place to go for upcoming events. YouTube is the place to go for past events. The blog and the newsletter is a place to go for updates, and we share, job postings and events and stuff on Twitter and LinkedIn. We use Big Marker for this presentation, and it has live captioning. So if you go to the very top, there's the word CC for closed captioning. If you click on it, you can see a live transcript at the bottom of your screen. We have a feedback form, which I will share the link to in the chat. And that's if you want to share feedback on this event, if you experience any technical issues with this platform, or if you have suggestions for future event topics. We have our upcoming May events are our Shiny extensions. And so actually what that is actually, I need to update that title, but it's building a Python app using Shiny, which I think is going to be a good talk. And then May 17th, we're solving NLP tasks, natural language processing tasks using LLMs, large language models. This is really big. This is by an NLP expert. And this will be of interest, especially with everything that's going on in the industry with ChatGPT and all. Today's talk is Data-Driven Mathematical Optimization, Pyomo. Jeffrey Kantor is a professor of chemical and biomolecular engineering at the University of Notre Dame. That's in Indiana, which is in the middle of the country, of the US. He does research and teaches in the broad area of systems control and optimization, applying these concepts to many different applications ranging from chemical processes, energy systems, finance, and control of complex natural watersheds. Professor Kantor received a bachelor's degree in chemical engineering from the University of Minnesota and a master's and a PhD degree from Princeton University in New Jersey, and a postdoc in the chemistry department at the University of Tel Aviv before joining Notre Dame. He has previously held administrative appointments at Notre Dame, including Dean of the Graduate School, Vice President for Research, Vice President and Associate Provost at Notre Dame, and visiting positions at Imperial College and Princeton University. You can find Jeffrey Kantor at JCKANTOR on GitHub. And with that, I am going to hand over the microphone and screen share to Jeffrey.
Well, thank you, Reshma. It's really a pleasure to be with you all. I'm very much looking forward to talking a little bit about Pyomo and what got me interested, and perhaps help some of you get started on your journey with mathematical optimization and Pyomo. I'm going to, let's see, share my screen with you. And let's see, I'll share this window. And if I've done this correctly, you should have a slide appear in your window, and we can get started from there.
Yes, I can see the slides.
Okay, great. Well, I thought I'd frame this as a series of questions and try to address an audience that I assume is very familiar with data science and all the tools and the many different and disparate technologies that go into data science, but perhaps has not been so familiar with a closely allied field, which is mathematical optimization and the tools that we use to solve these kinds of problems. So I'm going to take a little time to answer the first question of just what is mathematical optimization anyways, and then why Pyomo? Why is Pyomo what I think is a particularly useful tool for solving these problems? So I'll get a little bit of the why, talk a bit about what Pyomo is, give a brief introduction to some of the basic modeling objects that make up Pyomo, and then take a whirlwind tour through a few applications that I've been involved with over time. So, but before I go any further, I have to mention some colleagues who I've been working with lately on a project to really document what we've been learning about Pyomo. This is a group, Krzysztof Postek, he's now at the Boston Consulting Group. Alessandro Zocca is a young math prof at U Amsterdam. Joaquim Gromicho, who's professor of business analytics at the University of Amsterdam and has been a longtime officer at Ortec, one of the consulting groups in Europe, and then myself. We found each other about a year and a half ago and began working on a project to build a collection of notebooks and teaching materials. And much of what I'm going to say today is based on that project. And so I couldn't go any further without at least acknowledging them and all the many contributions to what I'm going to say today. So mathematical optimization, what is it? How does it compare with machine learning, which I assume many of you are already familiar with? And then some of this unique nomenclature that goes with mathematical optimization. We use the words objectives, decision variables, and constraints, and I want to make sure those are clearly defined before I go too further. And a little bit about how problems are classified for optimization. So first of all, kind of the relationship among these fields. I think of optimization as an allied field of machine learning and data science. Given this community's familiarity with data science, you're used to the statistics and visualization software and database softwares and the pandas and the data table tools that go into that. And that's certainly one important input and driver for optimization. The availability of data and the tools to manipulate and wrangle data have really, I think, extended optimization from areas where it was originally developed some decades ago into many, many new areas of application. And then I'd also like to relate it to machine learning, because so many of the machine learning algorithms and concepts are about optimization, pattern classification. Now I'll give an example of this a bit later. Regression and prediction. These are all problems or things where we can talk about the quality of a fit or how one classification is better than another. And whenever we can get into that kind of comparative analytics, then the natural question arises is how can we make it better? And that naturally leads into optimization. So I think of data science and machine learning as allied fields to this somewhat older discipline of optimization, where we're using mathematical models to describe business problems and then using algorithms to find solutions to those problems. So that's kind of how I fit it into this larger context of where I think this audience lives. And we use words like decisions, constraints, objectives, scenarios. These certainly have their analogs in other disciplines, but we use them in perhaps a particular way. First of all, with regard to objectives, When I think about the range of applications for optimization, to me, they kind of break out naturally into certain categories. I'm a chemical engineer, so for me, the physical world is very important. This is the world where we're trying to optimize processes and operations. We're speaking of managing inventories for manufacturing, blending operations and chemical productions, the scheduling of operations where time is a continuous variable. We want to order activities in a particular way to achieve an objective. So I think about those as physical kinds of objectives. In the financial world, it's all about the money. We have objectives trying to enhance growth of a portfolio, or maximize wealth and investment, or minimize risk in terms of hedging, or even determine pricing. So in the financial world, there's a natural series of objectives. And then I described kind of the information world, or maybe I could have titled this the data world, where machine learning and regression are the objectives. And we're trying to improve a quality of fit. And the outfall of the activity is to better organize data or information, or bestow the data with some sort of predictive capabilities. So I think about those as the kinds of objectives that we would try to formulate for an optimization problem. In terms of decision variables, we kind of have in the world of optimization, where we use a lot of computational tools and computational algorithms, we kind of divide it pretty neatly into a few categories. The continuous variables of time and components and flows, real numbers, if we want to, floating point numbers, if we want to think about it that way. These are variables that can take on continuous values. Then there's the world of discrete variables, things that we might model as integers or as discrete quantities. These come into play in a problem like strip packing, where we're trying to pack a number of objects into a set of raw materials, or into shelf space in a warehouse, or cut out patterns in either metals or fabrics. How many objects of each kind can we place into a box then has this integer quality to it. So we think of that as discrete variables. Our economic ordering, where we're trying to decide how many pieces of the raw material to order at a time and to meet certain schedule requirements. So that's a class of variables that we'd call discrete variables. And then there's the really intriguing class of Boolean logic, or true false, or yes no, or however you want to think about it, as do this or do that kind of decision making. This is the kind of decision making we do when we're trying to sequence activities, trying to develop and manipulate decision trees, or trying to make choices among alternatives, or trying to create a superstructure of possibilities, and from that select a path that provides a desired result. That's where decision making comes into play and interacts with these other kinds of things that we do with continuous and discrete variables. So in terms of constraints, there's no end to the words that we can use to describe the constraints that we need to deal with. From an application point of view, the constraints are usually imposed by time, by cost, by the finiteness of resources that are available to us. If we want to characterize them mathematically, we could say they're linear, nonlinear, convex, or not convex. If you want to think about them as not precisely known, we could think about them as uncertain constraints, where we have a bound, but we don't know exactly the limits on those bounds. We may have a resource available to us, but we don't know precisely how much of a resource, or we may have we may be appealing to customers and we don't know what the demand for a product might be. So and in this framework, we have uncertainty. We can speak of chance constraints, or probabilistic constraints, or deterministic constraints if things really are known. And then we can think about constraints organized in time. Sometimes we have decisions that have to be made here and now, um, in spite of uncertainty that we may face later, before that uncertainty has revealed itself. We have to make decisions here and now. And then we have decisions that can be wait and see. We can make some decisions now, and then on others postpone until new information becomes available to us. So we have this kind of sequencing of constraints, in the timing of it relative to information that might help us sort out these problems. So that's a very quick overview of the kinds of considerations that go into optimization problems. This is just scratching the surface. This is a very detailed slide. Perhaps you might have some trouble reading because it's so finely tuned, but I'll give a link to it into the PDF of this version. But this is one family, like I call it a family tree of optimization problems. At the very top is kind of this general and global idea of optimization, but then they come in different types. We can speak of convex optimization, or optimization under uncertainty, or nonconvex. These are very broad categories that break down further. When we speak of convex optimization, we could speak of, well, constrained optimization. And when we speak of those constraints, we could think about them as linear or nonlinear. And if we think about them as linear constraints, is the objective linear, or is the objective quadratic, as it might be in a financial application? So what's its mathematical nature, and what's the nature of the decision variables that are in which it's embedded? These are all considerations that help refine, help you to identify the kind of problem you're dealing with, and then find the algorithms that are specialized and can tackle and solve a problem of that character. So this family tree is complex. It reflects the complexity of the field, reflects the complexity of the applications that we attempt to solve, and it reflects our limited knowledge and our limited ability to solve these problems, and model and to solve these problems. We only break them down into this large family because we like to find, the more specialized we can be and the more structure we can find in the model, the more particular the algorithms can be designed, and the better chance you have of getting a solution to your problem. So this family tree often is important. It's important to practitioners of optimization. On the other hand, and one of the things I regret about the field, or one of the things I wish we could, as a discipline, help resolve, is make it a little less intimidating for people who are new. It's very easy to get lost in this and miss the forest for the trees. So hopefully, as we go through this discussion of Pyomo, it'll help kind of put these things back into a framework that's easier to work with. So that's a quick overview of optimization. Now, let me go to the question of why Pyomo? Why Pyomo? Well, first of all, what does it mean? Pyomo, it's a shorthand for Python optimization modeling objects. So as you all know, Python is an object-oriented language, and the original idea of Pyomo is to create some Python objects that would be helpful in the modeling and solution of optimization problems. So it's a very simple beginning, a very humble start. It's open source, so that makes it available to a wider group of people. Optimization languages have been around for a long time, and there are many of them proprietary and tied to a particular vendor of optimization software. So one of the things that makes Pyomo unique in this field is that it's open source. There are half a dozen major open source packages for optimization. Pyomo is one of those that's in the Python ecosystem, and I think starting to gain some traction. It's been under continuous development now for 15 years. That development has largely been a core group of developers at Sandia National Labs in Albuquerque. Their funding originally came from the U.S. Department of Energy. The Department of Energy was interested in supporting this work because the resulting modeling tools could be used to simulate new energy processes, new systems for creating energy materials, whether hydrocarbons or renewable materials. So this was originally developed as a tool for the analysis of alternative energy sources by the Department of Energy, but quickly expanded beyond that. The people who were involved with the development were largely a young group that had come from an optimization group at Carnegie Mellon, so they kind of had a very similar pedigree, and they thought of this as a way of bringing the technologies that they had developed and that had been developed over time in that group at Carnegie Mellon and a few other places into the broader Python ecosystem. One of the features that makes Pyomo distinct from many other modeling languages is that it's from the start a modular language. We can build models and then use those as components to build still larger models. And so that's one of the essential features that makes it scalable to really large applications. I'm a chemical engineer. We think about chemical plants and modeling entire chemical plants with a tool like this, made up of many thousands of equations. And that's entirely within scope of Pyomo. It's also solver agnostic. The optimization world is full of commercial solvers and open source solvers for solving linear programs, mixed integer linear programs, convex programming problems. The list goes on and on and on. Pyomo doesn't care which one you use. It supports, I don't even have a current count, but it's at least 20 solvers of both commercial and from both commercial and open source vendors. And that's important because it allows you to plug and play with different solvers and adapt a solver, find the solver that meets your modeling needs, not the other way around. So, so this, to my mind, is a significant part of the answer to why Pyomo. It's because you can build a model and then fit it to a solver appropriate for that model, and if necessary, change the solvers without having to change your model. So that plug and play capability is really important. Another feature that is unique to Pyomo, and I'm not aware of it as a feature in any other modeling language, is the ability to transform models. And I'll give a demonstration of this later. But the idea is that you can create a model using a suite of objectives, decision variables, and constraints, and then once the model is created, you can transform it into other models without having to worry about the details underneath how that's done. And I'll show you a few examples here in a few minutes. But what this does is it again greatly extends the utility of your models and allows you to match up with an even broader array of solvers. I'm a chemical engineer. I keep saying that because in so many ways it brings some unique aspects to the kinds of problems we have to solve. Among them are differential and algebraic equations. And one of the most important transformers that in my work is the ability to transform differential equations into a model that can be solved by these standard solvers. It's an incredibly important feature. And there's also a very active user group. There's a good online forum. You'll find the community is very supportive of one another. And if you have a question in Pyomo, regarding Pyomo, you usually can get an answer pretty darn quick if you just put a question out on the email list. So that's a little bit about why Pyomo. Now, what Pyomo? So what I want to do with the next few slides is just walk through a typical workflow and how you would go from a business problem to a solution using the Pyomo workflow. And this is a simple problem. I tried to find a problem I could fit onto where each part can fit onto a single slide. And so this is a very simple problem. It's a production plant. We imagine that there are 3 raw materials. One that's actually raw material, and the other are 2 forms of labor. I'll call it labor A and labor B. and we have some finite limit on the amount of labor that's available to us. Labor A, 80 hours at $50 an hour, labor B, 100 hours at a cost of $40 an hour. And we have two products, a product X and a product Y. Product X is higher value, but with limited demand. Product Y is a little bit lower, has lower price and unlimited demand. And the business problem is to decide how much of product X and product Y to produce in order to maximize the profitability of this plant. And inside the box, you can see the recipe that goes into producing the products from the raw materials. How much of each raw material is required and how many hours of each form of labor is required. So this is a simple problem. You could frame it in different ways. The most obvious way is to frame it as a question of how much of each product to produce. Alternatively, we could formulate it in terms of how much of each raw material gets used. We call that the dual problem, but for now we'll just work on the X and Y. And so the way the Pyomo workflow works is the first step is to convert that business problem into some sort of mathematical statement of what you're trying to achieve. This one's pretty simple. Everything's linear, so this becomes a linear programming problem. The idea is to maximize profit, and if you work through the arithmetic and the numbers in the chart, it turns out that there's a $40 profit for each unit of product X that you produce, and a $30 profit for each unit of Y that you produce. And so that's why the objective is 40X plus 30Y. The decision variables are the X and Y, so those are continuous decision variables, and they're subject to the three constraints I mentioned: limited demand for the product X, a limited amount of labor A that's required, and the limited amount of labor B that's required. The coefficients in those expressions come from the recipe, and the right-hand side of those inequalities come from the availability of the resources. So that's our mathematical statement. So that's why we call it mathematical optimization. We convert our business problems to a mathematical statement. And then in the Pyomo workflow, the next step is to convert that mathematical model into a description, into a set of modeling objects, and that's what Pyomo provides us. It provides us with a set of objects that we can use to create these models. And here I'm just highlighting a few. In the very first line, I'm using the concrete model object to create an instance of a model. So that's the very first thing. Then the next two lines are creating instances of the decision variables X and Y, and we use the dot notation of Python to append them as components to our model. And then we have an objective, and so that's another modeling object. The objective, we qualify it. We say that this is a maximization objective, so that's what we mean by sense. We declare these objects with decorators, so with Python decorators. So what the decorator does is it modifies the following function, the function that follows it, to be interpreted within the model as an objective. In this case, the objective is an expression that's 40 times X plus 30 times Y. So that's what the decorator does. It decorates a function that follows so that it's interpreted in the desired way, in this case as an objective. And then we have three constraints, and so we have each of them. We have a constraint for the demand, a constraint for labor A, and a constraint for labor B. We can name these whatever we like, and then those get appended to our model. So that's a complete Pyomo model for this business problem. So we're 2 steps into our workflow chain, and now the next step is to create a solution from this. And so this is the part where we specify what kind of solver we want to apply to our model. So we create the solver object using the solver factory method, and here we're creating an instance of a Gurobi direct solver. Gurobi is one of the preeminent tools in the logistics industry. It's a very high performant solver for linear and mixed integer linear programming problems. Gets heavy use in the all kinds of logistics industries, ranging from airlines to trucking and others. So that's how we specify solver. And then the solver.solve applies it. Says, let's solve this model. And then after the model solved, it's just a question of now how do we process that and turn that into useful information. And for a problem this simple, we can just simply print it. So we access these model components through a method. Each of the objects we've created and the modeling objects has a method associated with accessing the solved values, and we're using those here to print the profit and the corresponding values of x and y. So that's kind of a quick overview of the workflow chain. And just to kind of put it all together in a single chart, this is what it looks like. You have a business problem. First thing, that little figure down below is intended to be an analyst. It's a person like me or you, and we're sitting down there, and I'm calling that person our MO book because this is a figure that we will plan to use in our project. And the job of the analyst is to take that business problem, convert it first to a mathematical model of some kind using by defining decision variables and constraints and objectives, and then creating some Python code that will generate a Python model. And then from that point on, it becomes automated. That's what Pyomo does for us. From that point on, we let data drive it. So we call this data driven because what we're doing here is we're creating some Python code, mixing it with a source of data, whether that's in the form of a pandas data frame, a data table, or a SQL, or a query to a SQL, or to an online or cloud-based database. We combine it with data, and we let the data and the code create an instance of a concrete model. So the model adapts to the data that you have, and from there it's automated. We get a concrete model that's then we can transform in different ways. The little problem we just treated didn't require any transforms. It was already a linear program, so reasonably straightforward to solve. No extra effort was required. But we'll see an example in a moment where some transformation is necessary to make it solvable. So the first step is to transform it into something that the solvers can solve, and then we apply we mix that then with the solver, and we get a solution, and then we're back in the world of analysts and trying to take that solution information and present it in a way that's useful to our clients. So that's an overview of the Pyomo workflow. Now I'd just like to go through now just a series of short stories showing different applications. So let's just go through that. I kind of jumped right in.
Okay,
actually.
I found this on the web for a series of short stories showing it.
Okay, you just heard my Siri respond to the question I asked, so apologize for that. So I'm going to jump right in with a little modification of the story we just worked with, which was this small production plant that had two kinds of a raw material and two kinds of labor. Now let's do a what if extension of this. Suppose there's some new productivity, some new technology that's available to enhance the productivity of the labor bee. We have now a choice. Do we use the old technology or do we use the new technology? The new technology may be more cost effective, maybe reduce the amount of labor bee that's required, but maybe it's increased the skill level required, and so there's an additional cost as well. And what we want to do is we want to solve this what if problem, and we don't want to solve it by solving first one problem and then another problem. We want to mix the two together into a single problem, and we regard this as kind of a superstructure. We're saying that we've got this and we've got that. We could choose either alternative, but we would like to mix those together into a single problem that can help us decide in one swoop.
One moment.
That can decide in one swoop. What problem are we trying to solve? Or what's the best solution?
Still on it.
Okay, I'm sorry, I've got too many voice assistants in my room with us. Okay, so this is an area where we use what we call a disjunctive program, or where we could call this an either-or decision. And so the way that's presented here is we have a constraint, or we have two alternatives in the brackets. One is an alternative where the profit objective is the earlier one, 40x plus 30y, and the associated constraint was 2x plus y is less than 100. And then we have this alternative where the profit function is a little higher in x, because we're using a little less of labor B to do that, but in that it's only now an hour and a half of labor B that we're using. And so we have this alternative, and this is our superstructure. So can we solve that in one swoop? Now the symbol in between is the disjunction, the little v. The underbar means it's exclusive, meaning we get to choose one or the other, but not both. So that's the exclusive OR. And we'd like to incorporate that into our problem as well. Well, it's very hard to find solvers that provide a way to specify either or constraints or exclusive OR constraints. And so this is why the transformation capability of Pyomo is so darn useful. So here's the new model. This is the same as we did before, but with two changes. First is the introduction of a disjunction. And what a disjunction is it presents, instead of a single constraint in return, it produces a list of constraints. And it's a list of lists. So it's a list of constraints. In this case, there's a profit and a utilization of labor that are separate for each of the alternatives. And and each alternative is a sublist of this set of disjunctions. And so by putting this in, we've built in a decision-making element to our model. And now how do we solve it? Well, as I said, solvers that solve disjunctions are a rare breed. But what we can do is, through some standard modeling tricks, find alternative ways of expressing those disjunctions. If you happen to have some background in optimization, you probably remember the big M trick that allows you to introduce a binary variable to express the alternatives in a either-or situation like this. Or if you worked on this in more detail, you might be familiar with outer approximations or convex approximations to these kinds of constraints. There are a lot of different tools, but what Pyomo allows makes these problems workable within Pyomo is this idea of a transformation. And here we're using the transformation factory. We're applying a particular method from the generalized disjunctive programming module of Pyomo. We're applying the big M method. We're applying that to the model. And so what's going on behind the scenes is the model that we created, the one with disjunctions, is being converted to another model that's suitable for a linear programming solver to solve. And that's what we do. In this case, I'm using CBC, which is a cut and bound method for solving the mixed integer linear programming problems. It's a solver that would work here. Gurobi would work. Cplex would work. There are a number of solvers that would work. To test them, all I have to do is replace CBC with the name of another alternative and plug it in. I have to, of course, download it or purchased or found a way to access those solvers, but provided I have them accessible to me, I just specify which solver, solve it, and print the result. And so that transformation is what allowed myself as a modeler to efficiently deal with this problem. So here's another example of disjunctive programming. This is a strip packing problem. This is intended as a teaching example, so it's a fairly modest version of it. In this case, imagine this is a series of boxes, and you're trying to pack them into a shelf in a warehouse in a way that minimizes the use of shelf space. And so your alternatives are, well, here they're all just lined up at random, and takes, as the title says, it takes 897 centimeters to to put these boxes on the shelf. And the idea is, can we rearrange these boxes in some way to take less shelf space? So, and so what you can do, of course, is you can move them in the X and Y direction, or you can rotate them. And by doing so, try to pack them to the left of this shelf. Now, the same problem corresponds to cutting materials out of a sheet metal, cutting fabric for fabric and textile operations, or maximizing the utility of warehouse space. The strip packing problem is kind of an abstraction of a very practical and useful operations problem. So how can we model this? So in our workflow, now that we've specified the business problem, the next step is to specify the mathematical model. And I'll just kind of show that quickly. Here, our objective is to minimize the width. The decisions that we have are the X and Y location of each box. And so for each box, each eye, we have a left and right in X, and the top and bottom in Y. And they have to fit within the shelf, within the confines of the shelf. So that's one set of constraints. We have to position them so they fit in the shelf. The next set of constraints is they can't overlap. And so either one box is to the left of another, or they're in the opposite order, but never overlapping. And so that's an either or kind of constraint. So that's an exclusive or disjunction. And another option is one box can go above or below, but can never overlap. So again, either above or below. So the top of one box is below the bottom of another, or vice versa, but never both. So again, a disjunction. So we have a series of 4 disjunctions. And that's an intermediate line to rule out the possibility of overlap. And then we also have rotation. And so we can rotate a box 90 degrees. And that's a binary decision. Either rotates or it's not. And if it rotates or it's not, then it determines does X be, the roles of X and Y can be then inverted. And so this again is a disjunction. Either it's rotated or it's not. And that defines a different relationship among the decision variables. So this can all be packed. Now we'll do this one in 2 steps. This problem actually introduces the data-driven element as well, because what we have here is, obviously we don't want to solve this problem for just one set of boxes. We want to solve it for any set of boxes, and we want a data frame or a data table or some source of data to drive the model, drive the production of this model. And for that reason, Pyomo has a couple of other modeling objects, and that's parameters and sets. And these are the keys to building data-driven models. So by specifying parameters and sets, we can then start indexing the decision variables and start indexing the constraints. And we can create then families of constraints and families of variables. And so that's what's done here. What's not on the screen is the pandas data frame, which holds this data. You can see it referred to in the boxes.index, where we create a boxes set in Pyomo. So we create two kinds of sets. We create a set of parameters. We create a set of decision variables. And now this notation provides for the indexing of those decision variables and provides for establishing bounds on the decision variables. And in the last case, in R, it provides for specifying the decision variable as a binary rather than as a real number. So Pyomo has these features that are intended to support data-driven. The group I'm working with, what we like to call data-driven applications. And with that, we can then the modeling is just like before, except this time the decorators are indexed by the sets involved, and by indexing we can build these data-driven models. This particular application makes liberal use of disjunctions to avoid the overlapping of boxes and to allow for the option to rotate boxes. So, but this is the complete model. It's not that hard. And so once we've written all these things down, we've now expressed the strip packing problem, and here's the solution. So run this. Let's see. I left out the solver. I believe I used a CBC on this one as a solver. I used the big M transformation to transform this into something that a mixed linear programming solver could solve, and then solved it, and then presented the solution as this graphic. The green boxes are the ones that were just moved around. The red boxes were the ones that were rotated. And by doing all of this, we could find it on a shelf width of 266. It turns out the strip packing problem has a rich mathematical literature behind it. There are ways to estimate lower bounds. That's what that little green line is. And we can see that the optimal solution gets close to the green line, but not exactly there. So this is the extra information that we get from solving an optimization problem, rather than just relying on more straightforward mathematics. Now, I want to now just kind of move through a couple of quick stories, and then I'll try to answer your questions. These are all. This is a graphic that came from a cryptocurrency arbitrage study that we did, where the data set is a live data feed from a cryptocurrency exchange. This is a subset of the most traded currencies on this particular exchange. So there are, let's see here, there's 5, 10, 13 of these. Each of the red and green lines are associated with an ask and a bid that allow you to convert from one currency to another on this particular exchange. And then the challenge is to ask, is there a sequence of trades where you can begin at one currency, go through a sequence of trades, end back up at that currency, showing a net profit? Now, this is real-time data. This data is captured from a currency. We download a portion of the order book in real time. The model is a model that models the size of each order that's available to us, and the return that's available on that order. So each of these links on this chart corresponds to a few decision variables in a few pieces of parametric information in the model. The decision is whether is how much of particular order to accept, whether to place your own bid or ask to accept these trades, and how much. And then the objective is to maximize return. And so in this particular case, there's a trading cycle with a total of 8 trades that returns almost 15 basis points. Now, is that enough to cover the trading cost? That's an open question. But what it does point to is, in this particular example, at this particular snapshot in time, it points to an inefficiency in the market that is theoretically exploitable. So that's an example of an optimization calculation. Here's another. This comes from my chemical engineering background. This is what we call a pooling and blending problem. This problem demonstrates why Pyomo and not other languages. What's interesting about this one is, imagine that there are 4 farms, 2 that are local, those are the green circles on the left, Farm A and Farm B, 2 that are very far away, Farm C and Farm D, and each of these farms produce milk that has a certain fat content and at a certain cost. But the trouble is that the remote suppliers are so far away that they have to be put into a single vehicle for transport. So they're pooled and then brought to a location where they're then blended with the milks from the local suppliers to meet the particular requirements of each of the 3 customers. This turns out to be what's called a nonconvex program. It's a program that doesn't have a unique local optima. What this chart on the right shows is it shows the profit, how it depends on the composition of the pooled milk that's being transported. And you can see there's kind of peaks and valleys and dips and wiggles to this thing. It's not a linear program. It's not even a convex program. It's a problem that if you're only searching for local optima, you'll find 3 of them, and only one of them is the one that you're looking for. Modeling languages that are tailored to a particular solver, and if that solver is linear, you would not find an answer to this problem. If it was tailored to convex programs, again, you would not find a solution to this problem. This requires, this is in that class of nonlinear, nonconvex, with multiple local minima kind of problem. It's very easily modeled in Pyomo. It's not so easily solved. And so this is a case where being able to use multiple solvers is a very important feature. So I need to get on to questions here, so I'll leave it at that. I have a few more examples here of a binary classifier where we used an optimization model to model how a support vector machine type classifier can be trained using an optimization model, in this case a cubic one, and that'll work pretty well. Now I'm going to close by just pointing you to this particular repository. This is a repository for the data-driven mathematical optimization in Python. There are a series of about 50 Jupyter notebooks demonstrating the use of Pyomo to solve a wide range of different kinds of problems. There's an index at the end if you want to just search for a particular kind of application. I'll hit the index now, and you can see there's all kinds of applications to many different kinds of problems. And this is, if you want to get started on your journey down Pyomo, that's what these notebooks are intended to support. So, I'll stop there and try to do my best to answer your questions. Rashida?
Yeah, thanks so much, Jeff. You might have answered this question, but just to double check, somebody asked, is there a link to more complex Pyomo notebooks? Are those the ones that you just shared?
Yes, those are the ones I just shared. That's the MO book. You'll find a wide range of applications there. This is intended as kind of beginner to intermediate. If you're looking for a truly complex model, some of the models are up to several thousand variables. There's an economic dispatch for energy systems model in there. There are models that could easily be extended even further. But I think you'll find a lot of what you would need to get started on a more complex model. I think you'd find that in that collection of notebooks. There are a total of about 50 examples covering a wide range of application areas.
Oh, that's great. I think people would be happy about that. I had a question, which is, you know how like if you get a package from Amazon, it'll be like this huge box with a tiny thing in it?
Yeah.
Like, do you wonder like if Amazon uses this or not?
You'd wonder, don't you? in theory, yes. That's a 3-dimensional packing problem. How can you pack, if you've got a carton of goods, how can you pack them in, or you've got a collection of goods and you have to pack them into a box, how can you do that in the most economical way? That's the 3-dimensional packing problem. What I was showing in the example is the 2-dimensional case. To my knowledge, I'm not aware of this being done in real time for real, on large scale, like that kind of warehousing operation. I'm not aware of that. It's certainly within, the technology to solve those problems is certainly there. And I don't see any reason why you couldn't solve these problems on the order of seconds time scale. So I think the answer is there, but I'm not aware of it actually being done.
Okay.
Oh, here's a question. Any way can this be linked? Any way this connects or can be linked to quantum computing, as it is also helping with optimization? The answer to that is yes. Helen Durant, she's at Oakland University near Detroit. She's working she's a chemical engineer that's working on problems like this. The difficulty with quantum computing, though, is that we don't really have quantum computers available to us. There are simulations of quantum computers that are available to us. And are they faster and more reliable than the algorithms and the codes that are the result of 50 years of development? And I'd have to say the answer to that right now today is no, that quantum computing as a practical, everyday tool for solving real world problems, I think that's still a ways away, but holds great promise. Why it holds great promise is that some of these issues of convexity and non-convexity, local or non-local solutions, those can be resolved through the combinatorics of that can be resolved through quantum computing. So in principle, yes, it has great long-range potential, but I don't think it's here today. Okay. One question I have is, can you recommend a good framework book on optimization, something that gives a good overview of the optimization family tree? I recently read Algorithms for Optimization by Kokenfelder and Wheeler, but I'd like something more in depth. Thank you. Self-promotion here. This group of four of us, we produced this family of notebooks. There's also a text that goes with it. We hope to have a publisher for that soon, and I hope that's out the door sometime in the next 6 months, 8 months. So look for a book called Mathematical Optimization in either Pyomo or Python. We haven't actually settled on the title yet, and if the publisher likes it, you'll be seeing it. But that's facetious. But it's a good question. The one book I highlighted, let's see if I can share my screen again, and I'll go back to the slide, is was very near the beginning of my talk. Let me thumb to it. It's this one, Pyomo Optimization Modeling in Python. This is not a long book, but it's a book produced by the developers of Pyomo. It's now in its 3rd edition. And it covers a lot of interesting topics. The people on you can see there are a number of authors there. This is a very interesting and eclectic group of people. They're at Sandia, one's at Carnegie Mellon now, one's at a business profit at UC Davis. They're showing in this short book things like how to incorporate differential equations or how to incorporate stochastic programming. They cover a lot of ground in a few short pages. It's dense and it's particular to Pyomo, but I think it's an excellent introduction to a wide range of optimization topics. Okay, so here's another question. What are some of the challenging problems that you have solved in industry? Well, for better or worse, I'm not in industry, I'm at a university. But some projects that I've been involved with, some years ago I did one for a group in India that was was a version of the strip packing problem, where the idea was to take standard steel stock that comes from a steel mill and prepare that to cut that up into pieces that could be used to build electrical towers. And the issue was, how do they cut pieces to make the best use of the raw material and minimize waste? That turned out to be a large combinatorial problem. At the time, we did not use Pyomo. We used a version of a language called Ample. We used an open source version that comes with the GLPK package. It's called MathProg. It's a version that looks a lot like Ample. It gave a good solution that I understand is in use. So if I were to do it today, I would definitely use Pyomo as having a superior ecosystem, and it provides much easier ways to integrate data sources. So there's that. a project I was involved with a few years before that was a really interesting project. I don't know if you've seen the series Game of Thrones, or if you're a fan of that series. It's a series HBO or Netflix? HBO. So it's a fantasy series that takes place in a fantasy environment, and in the first season was successful, and they tried to build an ad campaign for the second season. And one of the features of that ad campaign was you could go to a website and you could repeat a chant that appeared in the first series. And the idea of the optimization was to synchronize an individual's chant with prior recordings made by thousands of other people. And the optimization problem was to take a new recording and break it up and add gaps so that it would synchronize with the other recording. And the effect was kind of a chant, mysterious sounding chant. So that's one of the that's easily the most unusual example I've been involved with.
One moment.
And another example.
I can't help you with it.
Another example was water management in a watershed that spans between the U.S. and Canada, and the idea there was to determine upper and lower bounds on a feasible set of operating plans for managing lake levels, a couple of lake levels. So those have been some things I've been involved with. Okay, so here's another question. Thank you for the great presentation. How was the performance of Pyomo in comparison with Jump? That's a great question. There's two parts to how Pyomo does its calculations. One is the formulation of the model. So we code in Pyomo, data enters, that's processed to create data that's then sent to a solver. So there's the model, there's the creation.
One moment.
There's the creation of the object that. There's the creation of the object that gets sent to the solver. And then there's the solver itself. Pyomo can be a little slow in the construction of a model and the evaluation of expressions. If you're in a situation where you have to do it in real time and repetitively in real time, it's probably not what you want to do. What you want to do is do a little bit more work and work in the natural API of the solver. This would be appropriate for real-time control of a robot, for example. That's a complex device with a lot of complex constraints, and it has to be operated on a sub-second time scale. So that repetitive kind of recompiling of a model in Python is not efficient. It would be a bad choice. Jump is somewhat better in that regard. It does assemble models a little bit faster. Jump is less able to, has fewer features for things like disjunctive programming. And in the end, when the model gets sent to a solver, it becomes the solver. If the solver is the bottleneck, so it kind of depends what the bottleneck is. If the solver is the bottleneck, there's no difference among any of these packages. So that's the answer to that. Just bought the Pyomo book. Good. That's glad to hear. What areas in industry, science, or life would you say pose great challenges, and which ones are showing promise in regard to optimization, supply chains, astrophysics, or communication? Clearly, supply chains have enormous potential for optimization. Also peril. Supply chains, as we all know, have global extent, and it could reach deep into a supply chain can get very deep and cross national boundaries very easily. Managing that supply chain can cross political boundaries and I think become very complex. And as modelers, I think we have to be attuned to where to draw the boundaries and what we do and not do in that regard. One example of that is a project that I heard described from Hewlett Packard. So this is public information. Their printers at one point were produced in Idaho here in the U.S. using parts from many different sources, some Far East sources and other sources. Their goal was to have as much flexibility in the production of printers as possible. So they wanted to produce printers in a timely way, but they wanted the supply chain to be backed up as much as possible. There's no sense in producing a printer if you don't have an order. There's no sense in producing a print head if you don't need to build a printer. There's no sense in building the components for the print head unless you need to build the print head and you have the order. So it's a backlog. And in the end, there's a warehouse somewhere that's storing raw parts. Now, where is that warehouse? And are the transportation channels reliable? Are they? Do you have that? If you're the operator, do you actually have control? Or maybe there's some other political. Maybe you're working in a political environment where you don't have absolute control over everything. So supply chains that cross national boundaries is one issue. I think if you're looking at other issues, there's a project at the University of Tilburg and now Amsterdam called Analytics for a Better World. I'd really encourage you to take a look. They're looking at things like supply chains to provide food assurance in global locations where that may not exist. So how do you provide food? How do you provide water? How do you make those supply chains effective and not subject to political interference? So Analytics for a Better World is a really good place to look for problems like that. So that was quite a bit.
Thank you so much. I don't see any more questions in the chat. Oh, wait, is there one more? Oh, yeah, that one is answered. Okay. Yeah, thank you so much for your presentation. We'll have this up on YouTube within a day. It was really, really quite informative.
Okay. Well, I hope it's what you're looking for. I took the point of view that help people get started on their journey with Pyomo and optimization.
Yeah, it was great. Thank you.
Okay. Well, thank you. Really appreciate the opportunity to be with you. Bye-bye.